So completing the square, we did that as bell work. We're moving on. Freeze it and try to understand what you're seeing there. Okay, so here we go. We're getting into the chapter now. Notice when you look at the sections, none of them say circles. It's because circles are not in this chapter for some reason. They should be. But then look at that good old White House. Nothing controversial about that place, right? Um, that White House itself, the architecture of it has many conic sections. That looks like kind of like a circle. There's something called the Oval Office, which is an ellipse, and so on and so on and so forth. Oval shaped lawn behind the White House, that's an ellipse. So don't write this down. This is just for your vision. I think I said this yesterday. Imagine two cups from a water jug. You know, when you get water from those, you ever see those little cone cups? Put right on top of each other. I don't know why. Someone just decided to do this. And then from these cones, we get conic sections. So this is the conic section. Down below here, I tried to show a circle. A circle, when I take these two cones and I do a cut straight across, that's a circle. So that's why a circle is a conic section. If I angle it a little bit, then I have an oval. All right, and then the oval represents an ellipse. And that's what we're doing today. If we cut through the top like that, that's a parabola. We're going to look at parabolas a little differently. And actually, we're going to have parabolas going right and left. So that is something that we're going to have a little different than our other one. And then weirdly, when I take one cut straight through the top bottom, it looks like I have two parabolas, but that's actually called one hyperbola. So again, I'm just showing you this to show you why they call it conic sections. They're cuts from cones, and then these shapes have many applications in the real world. For instance, I just told you about the ellipses. I just told you about an elliptical orbit is what our Earth does around the sun, and that's what we're going to talk about today. Parabolas are all over the place in architecture, and then some things in space have parabolic motion, like what are those called? Halley's comets. And then I know for hyperbolas, radio signals emanate out and through this circular thing, but the cross section of two radio stations, um, radio signals make up hyperbola, and then we can know what's going on with things and where they're located through that. So there's a lot of applications to it. And now I'm going to explain this on the board if you wanted to read this. And I'm going to have you help me. You're going to be my helper today. So I got to go over here and explain what makes an ellipse. So hold that real quick. Don't show your face though. You can sue me then. I got to make sure I have all my stuff here. My good marker. And then you have an eraser. So come sit in this seat and then make sure just face that screen towards me. What's going on in this class? Okay, so sit in that chair. I'll give you some space here. And then just turn it, keep that spacing that way. So go ahead and sit down, but keep that facing towards me. I'll tell you if you got me. All right, you got me. Okay, so now look at this. Oh yeah, nice. You can look up there and see if, but it's really the screen. Okay, you know, and I got to grab this real quick. And then Ivo, I'm going to toss you the eraser. Erase this other side so no one's looking at that. Here you go. Erase that side right there. This one. You know, for a circle, that if I just put this string, by the way, I ruined a pair of shorts for you guys. This was a string in my shorts. I pulled these out and had to throw my shorts out just for this demonstration. You're welcome. All right, so for a circle, you have a center. And then if I took this, yeah, you can just give that to me. If you took this string with this pen, that would draw a circle, right? You get it? Pretty simple, correct? And what's this string called? It starts with an R. 3, 2, 1, go. Radius. This is not what happens with an ellipse. I'm going to draw two different types to give you an idea that's important about ellipses. Instead of a center, I'm going to pull this out. Wait, 1, 2, 3, 4, 5, 6. I just know where kind of the midpoint is of this. I'm going to go approximately about this far. I want to make sure I'm centered here. In this first example, I took the center and I split it out a little far, but I still kept them kind of close together. So I want to show you the difference. This is how an ellipse is drawn. Tether this string and now do this. So it's similar to a circle string, but there is a difference. There's a big difference. Now I have to do this, otherwise, and I don't want to just pull that pin out. So I'm going to make sure this turns. There we go. And now this should meet over here. Boom. Nice. Boom. Does that look more like an ellipse or a circle? Be honest. 3, 2, 1, go. Circle. But it's not. I guarantee you that this is longer if I measured than this is because of the way this string works and the way that action works. That is why our Earth's orbit is nearly circular, but it actually is elliptical. From the casual eye, if someone could look at our orbit over 365 days, it would look like it was circular. But it is minorly elliptical. I'm going to need you to go to this side now. You can sit in your seat but angle the thing so that we're over here. Now I'm going to do this. 1, 2, 3, 4, 5, 6. Don't worry that I'm in the way. 1, 2, 3, 4, 5, 6. Okay, now I'm going to do this. You want to get nuts? Let's get nuts. Let's really spread these out. And then you really see the difference between these two ellipses. Got me on the screen? Good. Okay, tether. That happens sometimes. And now I try to draw this. I remember doing something like this when I was little. You ever do a spirograph? Kind of reminds me of that, doing this. Used to be fun. How many people did a spirographs when they were little? You know what I'm talking about, right? No? Oh, come on. Put your pencil in a hole, and then the thing would do different designs depending on the spirograph that you were using. Look more elliptical or circular? 3, 2, 1, go. Very much elliptical. This is called eccentricity, and I'm going to use this word today. And I want to write it down here. I'm going to keep this up here. Well, actually, I won't. I'm going to erase this one more time for $7. Tricity. This eccentricity, which weirdly, even after our chapter we just deal with, we do just use the letter E for eccentricity, is closer in this case to 1, to the number 1. And I'll show you that with our formula. The more elliptical it is, this is true. Coming over here, if you can just angle the thing, the eccentricity in this one is closer to 0. And actually, I can prove that when comparing an ellipse to a circle, because it's really simple, and that's why we keep these things together. So do write that down, and I do have it written down later. You don't even know what that eccentricity is yet. I just wanted to do that within those two different pictures that I drew. So this is what I actually did, and then maybe I'll have you draw this now. And go ahead and draw this. This is the creation of an ellipse. This is what happens. The red and the green is the string. And that rhymed. I'm shocked that that did. So the red is the string tethered to here. So what's true and what makes an ellipse is the distance from two, sorry I didn't say this word, foci. Can everyone say foci? 3, 2, 1, go. Foci. It's actually either foci, foci, or foci. I haven't heard many people say foci anymore. It's kind of weird. I've always said foci my whole career. Then when I watch videos, people say foci, foci. I don't care what you say. But the two focuses, that's what you can't say. That's not proper plural. Dictate the shape, not the center. So that's the big difference. So the reason these two distances are equal is because they represent the string in my demonstration there. And I always love that demonstration for ellipses showing the difference. Love that I have that string and I've had that. I've ruined those shorts like 8 years ago to do that demonstration, so it's okay. They was probably due anyway. But there is a center. There is a center as a starting point. And you're going to see, and I'm really going to throw it at you here, how easy ellipses are. If you actually have, at least today is. Tomorrow when we complete the square, not as so much. We'll have some issues on that. Today we're only going to be centered at 0, 0. We're going to take it slow, and the homework shouldn't really be that bad. Okay, so many different incarnations of that. We've already taken care of that. So here's what I want to compare an ellipse to begin with. I want you to write your circle equation again. So I'll have that for you, just as a reminder. But I'm going to do something weird with the circle equation. I can do whatever I want as long as I do it to, anyone? Both sides. Or the other side, correct, is same incarnation of that. So this is what I'm going to decide to do in this general form of a circle centered at 0, 0. I'm going to divide both sides by r squared. Ain't a big deal. Go ahead and do that real quick. Before you write your equation of an ellipse, that is still an equation of a circle centered at 0, 0. And then just for giggles, as your notes are going to continue tomorrow, remember a circle that's centered not at 0, 0, it's centered at h comma k. So I could do the same thing with that. I could divide both sides by r squared, and then that would be that formula. Because I think it's important to show the very slight, insignificant, minor difference between a circle equation and an ellipse. And I think you should be able to see it right now. Let's go to my pictures one more time. Is the radius consistent throughout this whole ellipse? Yes or no? Heck no. But you can think of this as two different radii. You can think that there is a center, and I have an x-axis radius and a y-axis radius. And those two radii are the same or different. 3, 2, 1, go. Different. In this case, the x-axis radius is longer than the y-axis radius. And then also notice where the foci are. Where are the foci? Are they on the longer of these two or the shorter? 3, 2, 1, go. Longer. That's because of how this all works schematically. I could have made these go up and down like this and put the text like that. Then your ellipse would have been tall and skinny. And I think you can visualize that. Just kind of messing around with that picture there. I'm glad I had that option. Can't you? Ooh, did you see the White Sox there? Nice. Okay, sorry. Here's your equation of ellipse. Ready? Okay, here we go. We're going to be centered at 0, 0, so it's more comparable to this. Tomorrow we'll do this when we change the center. So there we go again. Circle, ellipse. And I know it looks like garbage. I don't care. Circle, x-axis radius, y-axis radius are equal. The x-axis move is same as the y-axis move. Ellipse, the moves are different. That's why we have different letters here. That's why ellipses should be done right after circles. If you know circles, ellipses are a piece of cake. And this is my terminology that I'm going to use. No matter what is underneath the x squared, the square root of that number is the x-axis radius. No matter what is underneath the y squared, the square root of that is the y-axis move. Now, it just so happens in this first one, they're noting that the x-axis radius is bigger than the y-axis radius. So that is why this picture up here would result. This one, they're noting y squared over a squared. Sure, a is the bigger number. Then the y-axis radius is bigger. I could have put the tax like this and then used my string, and then this is what would have resulted. And then notice the foci are along the longer axis. It's because of how the drawing is constructed. Did I say this about Earth? There's focus. They're really close together. Do you know what the focus actually is? Starts with an S. What do we flip around? What do we go around? No, what's in the middle of our solar system? The sun. The sun is actually in a focal position. It's not perfectly centered. It actually wobbles. Actually, the sun's wobbles. That's how we found planets on other. Our first technique to know that there were planets in other solar systems is they could concentrate on that sun and see that it wobbles. The only way a sun would wobble is if gravity of planets around it are making it do so. And their math was so refined that they were able to tell the masses of planets around the sun and the way it wobbled, how many there were and what their masses were. And then they moved on to other methods that made that happen. That's from watching my space shows. Super, super interesting, the things that they can do. Now, the next part, this is going to look scary. This is why I have this all hacked apart, because I couldn't care less about a lot of this stuff. Doesn't that look scary and memorizing? And there's a whole bunch of crap here. I'm just going to destroy it. I don't care about the focal axis. I do care about the foci, and I do care about this term, the vertices. Do write that down. Vertices are endpoints of the major axis. This can be very easy to find. You're going to do this by graphing and just counting. And I don't care about you formally writing semi-major axis. What does semi mean? What does that word mean in math? What fraction is that? Half. So it's half of the length of the major axis, which actually is your radius move. So they come up with these terms. You'll be able to come up with them later. And obviously, I hope you know that the major axis is bigger than the minor axis. Doesn't that make sense? So in that drawing over there, the major axis is left-right. The minor axis is up-down, right? Actually, in that first one it is too because of the way I put the tacks, but it's hard to see that. You actually physically have to measure that one. So I don't really care about this either because I think you'll be able to figure that out. All I care about is vertices are those endpoints of the major axis, and then foci are this formula. So go ahead and write that formula down. And this should make sense. I'm going to tell you don't know this yet, but C is our focus move from the center. C needs to be smaller than A. I'm going to show that over here right now. And then this is why your formula should not be something you have to memorize. Oh, can you get me that marker real quick? I think there's a marker on there. Last hour, it didn't work out so well because this was brand new. Can you hold it and angle it so it's right on there and then look at that? There we go. There's a big shiny thing there, though. So here's the center. This is going to be A because this is the longer of the two radii moves. This is C. This is what C is going to be, the move to get to the focus. Why does C have to be smaller than A? Because of the way this is constructed. There is no way that this could be outside of that. So what I'm telling you is what guarantees that? The operation of subtraction. When I subtract from A squared, so A squared minus B squared, that makes sure that this is smaller than this. Another way of thinking about it, what did I say the sun is? It's a what for the Earth in its elliptical movement? The focus. Does our planet go like this? Here's the sun, and then the Earth goes like this. Is this what happens? Is the sun outside of our orbit? Heck no. Our sun is inside our orbit. That's because it's in a focal position, so it must be inside. So it's not memorization. Evan. Oh, that used to be McLaughlin. No, her as a dean. She used to highlight something. Okay, so one more thing. Here's that eccentricity thing. And we can write it one more time. Here's what eccentricity is as letters. C over A. Focus move divided by longest radius move, whether it be up, down, or right, left. And I already put that up there and I already put that with our drawings over there. You need to know where I came from. I came out of left field on that, but I wanted you to see the two different drawings. I wanted to see when the foci were close and the foci were far away. Close, more circular, far away, more elliptical, with the string being the same length. So what do we got? We got not a circle. We got different radii values. It's going to be really easy to graph these. We got to find a focus. It's a formula. And then we got to know what eccentricity is. So it's a couple different things in formula land that you got to memorize here. Okay, then I'm going to go to this first one and then be a little jerky on it. Y squared over 25, that's easy. Plus x squared over 21. Bummer. Equals 1. Okay, so in some different teachers' writing, I think this might be, I don't know who this is, old notes. The larger number is under y. So the y-axis is the major axis. All right? You have a bigger move. The tacks would be like this. I would have put them like this on the board. I should have done that one time. Then one ellipse up, down. What I would have to do is put the tacks like this, and then you would have a tall, skinny one. That would be the construction of it. But everybody should know the y-axis radius simply. What is the y-axis radius? 3, 2, 1, go. I only heard one person say 5. I'm going to throw up. It's the square root of 25. Remember, I just put that up there. This is a squared. A is the move that I'm going to do just like in a circle. Just like in a circle, you got to take the square root of that, just like r squared. Malik, you're not sleeping, are you? You kind of were. You look awfully comfortable laying on the trough of my chalkboard over there. It's not a chalkboard. It's, what's that called? Whiteboard. Thanks. You always got all those answers for me. Okay, here's the problem with the 21. What do I have to do to the 21? I have to take the square root. So actually, the x-axis radius is the square root of 21. And I did get this last hour as being 4.6-ish. And guess what? You got everything you need in order to graph this. By the way, everything is going to be 0, 0 today. And you should know that. It's easy. You don't have an h and a k value like with circles. Right? That's the only difference you're going to see tomorrow. So recognition. Okay, so what do I have to do to draw this? The y-axis radius is 5. From 0, 0, I go 5 up, 5 down. And then the x-axis radius, not as nice. It's 4.6 right and 4.6 left. Sort of elliptical, but more circular. Your eccentricity value is going to be on the small side. Probably swinging closer to 0, but we'll look at that later. And then what do you need for the focus? You need this formula here. And why do you need to find the focus? Because it's what generates the picture. So that's what we need to understand. C squared equals 25 minus 21, which is 4. Square root of 4 is 2. Now, I already drew it, but where do the foci belong? And the foci belong along the major axis. It's because of how I constructed the thing. I wish I would have turned it, for the third time saying I could have put the tacks up and down. Then I'd have a parabola that was tall and skinny. So the foci are actually 0, comma, plus or minus 2. 0, comma, plus or minus 2 for sure. All right? All right. One more thing you could find is eccentricity, which I will find off to the side here. Hate that we have the word E again in there, or the letter E. The letter E. I feel like Elmo whenever I say that. C over A. C is 2. A is 5. The bigger of the radii values. 0.4. Anytime you get, we're going to have one later that's like a eccentricity of 0.6. And it still really isn't that ovular. 0.8, 0.9, those where we really get a good look of an oval going on there. Okay? And that's it. There is nothing else that could be found. Okay, here's what I mean. What's the length of the major axis? How long did my finger just go? How many units? 10. What's the length of the minor axis? That's a pain. It's 9.2. Sorry, that's a decimal. What's the semi-major axis? 5. This is why I don't think we have to write these terms down. It's kind of silly. And I can't think of anything else. You know what else they do though? They do call this, these are the vertices. So let's put that down real quick so we have a term. Oh, they're up here. Vertices, endpoints of the major. Oh no, that's for the next one. I'm a maroon. It's 0, comma, plus or minus 5. These are called the co-vertices in other books. Oh no, why is this? Okay, good Lord. And now my phone's going off. I get sounds going all over the place here. I gotta turn that off by my friends. And that's my daughter, actually. All right, and this is plus or minus 4.6, comma 0. So these are other things that we could ask you. I know I threw out co-vertices. Other books call it that. They just call it the endpoints of the minor axis. So just be aware of that term as well. Okay, all right, so why is this one not in the correct format? What do you think I have to do to both sides? What do I have to do to both sides? Okay, we'll put that back. Divide by, what do you think? Divide by what number? There's only one number on the right side, so what number is it? 36. But let me do this real quick. Let me show you the difference. What would that be an equation of right now? If I did that, what would that be an equation of? Circle. What's the radius of the circle? You better know that, otherwise we got a lot of problems. All right? Because I can't do ellipses if we can't remember circles. This is building on things. All right? So that would be a circle with a radius of 6. This is the difference. See, this is why we have to divide. The reason or the fact that these have two different numbers in front of the squares make this not a circle. You're going to have different radii values for the x-axis and y-axis. So I have to divide by 36 and then see, oh, okay, because we have different numbers in front of x and y, we now have different numbers underneath x squared and y squared. I should have said squared. Oh, I'm going to jump out the window if we don't get this right. Maybe you just want to see me jump out the window. What's the x-axis radius? 3, 2, 1, go. 3. What's the y-axis radius? 3, 2, 1, go. So to graph this is like the most Mickey Mouse thing ever. I can just go here and go here and go 1, 2, 3 to the right, 1, 2, 3 to the left. And now I can answer, what are the vertices? Plus or minus 3, comma 0. What are the endpoints of the major axis? Plus or minus 3, comma 0. What are the endpoints of the minor axis? 0, comma 2, 0, comma negative 2. What are the co-vertices? Same thing. I know co-vertices I just threw out at you, but we're doing this simultaneously with my Math 2 students, and their book calls these the co-vertices. So vertices, co-vertices. I'll write that. Covert operation. And then these are called the vertices. Just for terms. I hope you know that that's vertices. I don't have the time to write all that. So our x-axis radius was 3, our y-axis radius was 2. The only other thing that you got to do is find the foci. Where should the foci be? Right, left, or up, down? 3, 2, 1, go. Ah! Which one's the longer axis? Right, left, or up, down? Right, left. So the major axis is this axis. By the way, what's the length of that major axis? If I asked you that, 3, 2, 1, go. 6. It's just counting. What's the length of the minor axis? How far is that? 4. I mean, this is so Mickey Mouse. These questions we could ask, you just got to know the terms. Oh, so I actually did do that. Vertices. Vertices are plus or minus 3, comma 0 if you wanted to care to write it down. But here we go with the foci. 9 minus 4. Oh, my goodness, that's a computer. 9 minus 4, which is 5, square root of 5 when you're done. Okay, which way do I move square root of 5? Right, left, or up, down? 3, 2, 1, go. Right, left, because you're on the major axis. So actually the foci are plus or minus root 5, comma 0. If you don't write them as vertices, you will be marked wrong. And that is true. Because you got to tell me that you know which axis it actually belongs on. So a lot of stuff goes on with conic sections, a lot of review of dealing with a coordinate plane. That's really a big deal. Completing the square that I started with, that's some algebra.